Hello everybody. I'm Pascual Cantos from the University of Murcia, and my talk is entitled Do We Really Need Mathematics in Linguistic Studies? Well, the use of mathematics started in the 40s and the 50s by George Zipf. He wrote a really cutting-edge book, which was the Psychobiology of Language, in which he established what has been known for many decades, Zipf's law, which essentially says that the frequency of a word is inversely proportional to its rank. Now, what does it mean? That means the following. Suppose you've got your 5 words, 5 Spanish words, de, pero, mi, normalización. That's the frequency of occurrence of these words in the corpus, and that's the rank position they occupy, which means that the most frequent word, which is rank 1, is de, with nearly 10 million occurrences. The word in position 75 is the conjunction e, with roughly 124,000 instances. Okay, so you see here that when the frequency decreases, the rank increases. Furthermore, if you multiply the frequency by the rank, you get more or less a constant value, which is roughly between 10 and 11,000, which means that if you multiply the frequency and the rank, you get a constant value. Now that's very important, and the most outstanding thing about this law is that it holds for any language. So essentially it means that if a word is positioned in number 1 or rank 1, the frequency of the second most frequent word is half as much the frequency of the first one, and a third of the first one, the one in position 3. Okay. Visually, you can see it far more clearly if you, like in this graph here, if you display in the y-axis the frequency and in the x-axis the rank. So you have here that words positioned 1 or words positioned in a very high rank, they are very frequent, whereas words which are positioned at the very end of the scale, that is position 300, have a very low frequency. This means that in a language you have very few words which are used a lot, and many words which are used very little. Okay, right. If you now transform the frequency values and the rank values by means of a logarithm, what you get is a regression. You get a straight line with a negative regression. Okay, and this means that in a way we can model languages. You can model mathematically languages in many ways. And that's the principle why we can use mathematics in linguistic studies. Okay, what I'm going to do now or next is I'm going to focus on different research areas I have been working on, particularly using quantitative methods, statistical and or mathematical models. Okay, and the areas are computational lexicography, forensic linguistics, clinical linguistics, and others such as stylometrics. Okay, now the first one is computational linguistics. In computational linguistics, among other areas, I've used mathematical models to model lexical growth. Okay, now before we start, I just want to give you some hints or some ideas, some basic notions about 3 concepts: tokens, types, and lemmas. Tokens are actually the number of words in a corpus, so the number of words in a corpus grow linearly. The second notion is types. Types are different word forms. This means that when you have a corpus, at the very beginning, you are constantly finding new words, or new word forms, if you like, or types. But it comes to a point where all the words or all the word forms have already occurred, and you start finding less and less one, until eventually you come to a line which becomes straight, which is parallel to the x-axis, which means that the types don't grow. And they simply don't grow because all the types or all the word forms have already occurred. So you enlarge your corpus, but you don't get additional information because you don't find more words, right? And the second notion is lemmas. Lemmas is actually the same as types. The only thing is it refers to the canonical form. So for instance, if you look in a dictionary for the word raining, you won't find it. You will find it as a lemma reign or under the lemma reign. Okay. Now, the revealing thing about lexical growth is that lexical growth is idiosyncratic. Okay, it refers to individual people. It refers to individual authors. So, for instance, if we study the lexical growth of different authors, we see, for instance, that Conrad has a much greater lexical growth or lexical density than Shakespeare or Doyle, for instance. The important thing about these revealing findings is that we can model the lexical growth of any person, any author. And this gives us a regression like this one here, where you can see this is taken from Alice in Wonderland. So you see that Alice in Wonderland, the number of types is equal to a constant value multiplied by the number of tokens to the power of, well, roughly 0.5, or if you like, the square root of the tokens. This means that if you were to take 60,000 words from Alice in Wonderland, you can more or less predict, without actually using any concordance programs, that the total amount of types could be roughly something like 8,200 or something like that. Or furthermore, you could say, yeah, what about if Alice in Wonderland were 1 million words long? You could perfectly know beforehand how many different types, and of course also lemmas, these would entail. The positive thing about this is that you can, without actually the need of compiling a huge corpus, you are very likely to know how many, how much or how many words the corpus needs to entail in order to get a specific number of different words. Okay, this has been applied by means of a hierarchical cluster analysis to differentiate different areas or different domains, linguistic domains. So, for instance, here we have applied the lexical growth model to geography texts, history, natural languages, medicine, philosophy, chemistry, physics, computer science, mathematics, architecture, and sociology. So you see, for instance, and that's interesting, that texts among geography, history, and natural sciences have a very close lexical growth or lexical density. They are very, very similar. In contrast, we have that medicine is quite similar to philosophy. And, for instance, chemistry is very close to physics and computing, right? And you also see that medicine and physics are much more related as regards to lexical density to geography, history, and natural sciences than, for instance, to chemistry, right? And you see that mathematics is far more closely related to computing, physics, and chemistry. And on the other part, we see that architecture and sociology are two types of linguistic domains which are completely different to all the other ones, right? So you see here that basically you have sort of 4 families. You have a family of linguistic domains which are very similar in lexical density, which are geography, history, natural language, natural sciences, medicine, and philosophy. And then on the other hand, you have chemistry, physics, computing, and maths. And the last one, architecture and sociology, which are very, very different to the rest. And you see this because they enter with the other groups at the very end of the scale, right? A further use of mathematics in linguistic analysis has been, in our case, forensic linguistics. We have used forensic linguistics in order to detect deception, right? The research we carried out here was by means of something which is known the linguistic inquiry and word count, right? This is a database which essentially contains 2,200 words and lemmas which are grouped into 75 categories and which are furthermore divided or classified into 4 dimensions, which is the standard linguistic dimension, the psychological dimension, relativity or relative dimension and the personal dimension. Okay, essentially each dimension refers, for instance, that the I'm sorry, this is in Spanish, but it's no problem. The first dimension, which is the linguistic dimension, there you have, for instance, word counts, you have the percentage of words with more than 6 characters, number of pronouns, first person singular. In psychological processes, you have, for instance, positive and negative emotions. In relativity, you find, for instance, space, you have, for instance, movement, you have tense and time. And in personal issues or personal affairs, you have occupation, you have hobbies, you have financial issues, and so on. So words and lemmas have been grouped according to these 4 dimensions, and furthermore into these different categories. What we've done is we've taken these categories and we have counted the following. We have used a very sophisticated software which is called Linear Support Vector Machine. Essentially what it does is it's a machine learning approach, and it classifies texts. In this case, it classifies whether a text is true or a text is a lie. Okay, and how did the software do this? Well, what we did was the following. We took 100 informants, right, and we asked each of these informants to write 2 essays in approximately 10 minutes. And in these 2 essays, they should choose one of these topics, which was own sexuality, bullfighting, best friend, and best school teacher. And they had to write 1 text telling the truth about their own sexuality, bullfighting, best friend, and so on, but also lie about the same topic. Okay, so for instance, if you choose bullfighting, you have to write the truth about bullfighting, what you think and what your feelings are about bullfighting. And then the next essay would be an essay on bullfighting, telling just the contrary, just to trying to lie. So if you're against bullfighting, you have to write an essay saying that you are in favor of bullfighting, that it's a national tradition and it should be kept, and things like that, right? So at the end, we know a priori which text is true and which text is false. What we have done is we have trained this SVM machine or machine learning approach by means of taking not 100 but just 50 informants. So we have trained the software with 50 informants, and then performed the analysis with the remaining 50 informants. To see whether they were correctly classified as correct or incorrect, or if you like, truth or deception. And this is what we got. We found, for instance, that the best dimension on its own was dimension 2. Dimension 2 correctly classifies roughly 68% of all the texts. Okay, remember that the dimension 2 was the psychological processes. So by means of psychological processes, okay, you could more or less distinguish 69% of the cases whether it's true or not correctly. The lowest performance was achieved with dimension 3, which was relativity, which is this one here. So we have that relativity is roughly 60%. Okay, and the best combination of dimension was the one by 1, 2, and 3, which were standard linguistic dimensions, psychological processes, and relativity, where we got an average of 73.1%. Okay, you can see that the different dimensions don't work exactly the same depending on the topic. So for instance, so dimension 1 is very positive, for instance, to tell you the truth about best friends. Okay, whereas the combination of dimension 1 and 2 is particularly good for to tell you the truth about best friends. Okay, others, for instance, if you refer, for instance, to bullfighting, so you might see that the best approach would be this one here with dimensions 1 and 3, which is standard linguistic dimensions and relativity. Okay, that's very interesting because this training achieved very high in specific domains and specific combinations, right? And this is extremely positive, for instance, if you use it, for instance, in police stations, right? To know more or less, or with a certain degree of certainty, to what extent the individual is telling you the truth or lying. Okay. Another approach using mathematics has been clinical linguistics. In here, we apply clinical linguistics in two different areas, in Alzheimer's disease and also bipolar disorder, as we'll see afterwards. Well, Alzheimer, as you know, is a progressive and irreversible decline in a range of cognitive abilities, right? As the disease progresses, as you all know, nerve cells shrink and die, and also the surface of the brain becomes smoother. This is a healthy person and this is an Alzheimer affected person. So you can see the dramatic differences between these two brains. Okay. Now, Alzheimer's disease early symptoms, as you probably know, are memory loss and minor forgetfulness. But these symptoms become steadily more and more dense when the illness progresses. But the important thing, what we established here is, can we in some way detect whether a person is in an early stage of Alzheimer that is preclinical, before actually it has been diagnosed, right? The problem is that there are no reliable diagnoses and there are no reliable methods to know whether a person is prone to be affected by Alzheimer or not. Okay, so what we focused now, we analyzed different people, and what we wanted to get texts and getting linguistic production of these people, and to see whether we could approach this. And we found something very interesting. We found an article and a number of papers on Harold Wilson, which was a prime minister. And in these studies, they concluded that Harold Wilson resigned as prime minister because of an early stage Alzheimer's disease. So he realized that something was going wrong with his brain, and he simply resigned. Well, what we did is we tried to identify linguistic variables likely to be altered due to the Alzheimer affection, particularly at the embryonic stages, at the very beginning. So we focused on this case study, and we tried to replicate the study we read of the former British Prime Minister Harold Wilson. Okay, the methodology used was a longitudinal examination. So we contrasted all his periods as prime minister that ranged from 64 to 70 and 74 to 76. Now, 64 is the year he entered office as prime minister, and 76 is the year he resigned as prime minister, right? Which he seemed to have some mild cognitive impairment at this stage. Okay, the data we collected were his oral outcomes. We extracted the information from the Hansard corpus. Now, the Hansard corpus are transcript of all spoken activity in the two houses of Parliament. The important thing about these statements is that about these speeches is they are not statements, and all the oral productions are spontaneous. Nothing is read, so it's all spontaneous interaction between Harold Wilson and the rest of MPs. So we have in total 10 periods of contrast. So we selected randomly 25,000 tokens or words for each year. So remember, it was spontaneous speech and verbal exchanges. We deleted any statement or anything that was read aloud. Okay, and this is how it looks like. Okay, this is a transcript of 10th November 64. and sorry, 10th November 64. Okay, so you see here that this is a question, right, which is addressed to the Prime Minister. This is Harold Wilson. This is the question, this is his answer, this is a follow-up question, this is again an answer. Well, what we did is we selected only the Prime Minister's interactions, right? Okay, and compiled a corpus, so 25,000 words for each period. Okay, the variables, there is no consensus about the variable. Okay, and we found nothing that was actually definite about the variables. So what we did is we simply used all the variables that had been used before, but never in combination, right? So we use punctuation variables, lexical distribution variables, frequency of occurrences, so the 30 most frequent words, the 30 most frequent content words of Harold Wilson, the eidetic marker, not just person, but also place they exist, the use of pronouns versus nouns, that is the relative relationship between them, part of speech distribution, and hapax-legomena. Hapax-legomena are words that occur a single time in his speech or in his speeches. Syntactic complexity, conjunctions, the use of conjunctions, repetitions, right, that is engrams, that is the use of two consecutive words, the repetition of these two consecutive words, 3, 4, up to 12 consecutive words, and then the use of indefinite words or indefinite pronouns such as someone, anyone, anything, someone, something, and so on and so on. Okay, and I'm just going to focus on some of the differences found. Okay, now we found statistical significance in punctuation variables. So we saw, for instance, that semicolons decreased dramatically. Semicolons are this one here, the blue one. So you see it decreases with time. It starts decreasing from 64 to 78. Now the important thing about semicolons substitutes conjunctions. So semicolons are normally used in very long sentences. You have a very long sentence, you don't end the sentence with a full stop or the use of a conjunction. What you do is you use a semicolon, right, and carry on with the idea within the same sentence. This means that his sentences were very long in 64 and became shorter and shorter in 76 because of the lack of semicolons. Similarly, colons here, which are depicted, semicolons, yeah, these are semicolons. Colons are this one here, right, the pink one. It has also decreased, right? Semicolons are very characteristics at the beginning because Harold Wilson had a prodigious memory. He remembered literally word by word anything which was said by his political enemies, right? And furthermore, he could actually quote the classics and quote 10, 15 lines of classics, even in Latin. And this is something he can't do towards the end. And another interesting thing is the drop of questions, the use of question marks, the drop of questions, sentence in questions. Though here it's not statistically significant, but the drop is important. So what we did is we analyzed questions further on, and we saw that actually the decline is not just in the amount of questions, but also in the variety. So in 64, he used, for instance, absolute questions, relative questions, alternative interrogatives, tags, and other types which are affirmative into with question annotation. But in 67, he essentially just used absolute and relative questions. So it was not just the amount, but also the variety of questions that decreased statistically significant. Another very revealing finding was the overuse along the years of the pronoun you. The pronoun you, which was the pronoun you refers here just to singular, so we contrasted and we looked all the instances of you to make sure it was singular or plural, and it was just singular. It was very revealing, because what this reveals actually is that his discourse universe starts restricting just to speaker and hearer. The overuse of you is also accompanied with nearly complete absence of any other pronouns, such as we, they, she, and so on. So it's essentially restricted to you, addressing just to the person, to the person who he's speaking to his hearer. But in addition, you becomes also a substitute of honorable friends, of MP, and also the name he used to address the specific name, or county he used to address his opponents. No more present. And the very revealing thing was that the engrams. So you see here, now engrams, as I said just a minute ago, two engrams are two consecutive words which are repeated in the discourse. Three repetitive words, three consecutive words which are repeated, four, and so on. So if you see, for instance, Harold Wilson's 64, which is 6, this one here approximately, so the longest stretches of text were 10 words with a very low frequency, right? But as he approaches 75 and particularly 76, you see that he keeps repeating structures with 12 consecutive words, exactly 12 consecutive words for many times. So very high repetition of fixed and cognitively very undemanding structures, right? So essentially the conclusions were that he might have some presence of some degenerative neuropathology in the 60s, when in 76 when he resigned. So, and the revealing thing is that he accessed more and more common frequent words. He used repetitively prefabricated chunks, the engrams I just mentioned, and he resorted to less complicated syntactic structures, and this is particularly revealing in the less use of colons and semicolons. Okay. A further approach using statistical methods has been in clinical linguistics, the study of bipolar disorder, and we concentrated here on the case of Edgar Allan Poe. Okay, now bipolar disorder or manic depressive disorder is a clear mood disorder that shifts from euphoria to depression, and it changes very rapidly. Okay, now our starting hypothesis, to make it short, is that Poe's cyclothemic disorder, that is his fluctuation from euphoria to depression, is reflected in the lexical change and lexical choices he makes along his tales. Right? So our methodology was quite similar to the one used with Harold Wilson, which was longitudinal. Okay, we don't have oral production of Edgar Allan Poe, so instead we used his tales, right? And we try to look for whether these episodic mood fluctuations, right, were present in his tales and how to measure them. Well, these are the tales. The tales were ordered chronologically. Okay, we extracted 47 out of his 60 tales, right? The date here, okay, is not necessarily the date of publication, because he wrote some of these tales before and published them afterwards when he was short of money. So this is actually just the date of publication. So you see that here, for instance, in 1831, he published three tales, and they ordered. This was the first one, the second, and the third, and so on. There are years which he has just a single one, right? For instance, here in 1840, here's just a single one, well, the man in the crowd. The variables we used were completely different because personally I wasn't very much interested in using more than 3,000 variables as I did in the Harold Wilson study. So here I concentrated just on eight standard corpus lexical measures, which were lexical richness, which is the ratio between type token, but the standardized one, okay. Content words, that is the ratio of noun, verbs, adjectives, and adverbs. As for the mental lexicon, okay, we study the mean of word length, long words, the number of long words, words with more than 10 characters, hapax legomena, hapax, that is words that occurred a single time in the tail, and exclusive hapax legomena. The difference is this: these words occur a single time in one tail. These are words that occur a single time in any of the tails, right? And finally, the lexicosemantic text difficulty, or text complexity, or syntactic complexity, if you like, which is the mean sentence length given in words and the automatic readability index. Now, this tells you how difficult a text is for reading, okay? And this is how we proceed. So in a normal distribution, we calculated the normal distribution of Edgar Allan Poe. So what is normal in Edgar Allan Poe? So everything which is here on the blue shadowed area, this is normal, and this is abnormal. This is very low compared to the normal behavior of Edgar Allan Poe, and this is very high or far or very distant from what has or what is considered normal. Of course, the normality, normality is different in each speaker, right? So we, using all the data, using all these 8 variables, we calculated the normality for Edgar Allan Poe. And what is important for us is this. This means that if it's below the mean and very above the mean, these indicate fluctuations. This is either euphoria or depression and euphoria. And these are the elements that interest us. Okay. Just to give you a taste here, for instance, that's the automatic readability index. This is about the difficulty of reading novels or tales written by Poe. So you see that everything which is above 2 and below 2 are not normal for Edgar Allan Poe. This means, for instance, that this one here in 1841, which is this one here, The Man in the Crowd, this tale is, compared to other tales of Edgar Allan Poe, a very difficult one to read, right? Similarly, this one here, which is roughly 1831-4, which is this one, The Man That Was Used Up, this is comparatively very, very easy to read, okay? Or this one here, which was in 1849, which is this one here, Landor's Cottage, is a very difficult novel to read. Its complexity, lexical complexity, and structural complexity is very strong. So this is comparably a very difficult, whereas these one here are very easy to read ones, right? So you see here the contrast, the euphoria and depression periods, okay? This is the data, okay? The green shadowed areas or green shadowed measures show normality. This is normality, okay? This one here is, you find here some anomalies, right? So the blue ones are above the mean and the red ones are below the mean. So everything which is superior to 2 is not normal. Less than -2 is not normal, right? But what can see here, apart from minor periods, okay, which is this one here, this or that, we clearly see here 4 periods, 4 consecutive periods. You see here that at the end of 38, beginning of 1839, A longer period is at the end of 39 towards the end of 41, okay, constant alterations here. Then a further period which is beginning or mid 42 towards the beginning of 31 or 43, and then the most prominent one, which is here from 46 towards the end. Okay, the interesting thing is we can perfectly see here four different periods, which are full of euphoria and depression. And if you analyze these four periods coincide exactly with the four most prominent periods of his life. This one here, period 1, which is 38 towards early 39. Poe and his family moved to Philadelphia the year before going to New York. He's worried about his family and he married in 36. So it was a sense of depression but also euphoria, right? In 39, late 39, 41, which is period 2, right? In 39 he published a book with commercial success, which was The Raven, right? And euphoria may prevail in this area with some depression periods. The third period, mid 48 towards early 43, he leaves Graham's magazines unwillingly. He was actually kicked out, right? And depression prevails. And finally, the last period, which is very intense, which starts mid 46 towards towards 49, which is his death. His wife died in 47, and the previous year he was full of debts, right, and a very depressive state, right. So the interesting thing is we have joined here quantitative data with qualitative information, and as you can see, they match perfectly, and this is very stunning. And a further example is on stylometrics. Okay, on stylometrics, I would like you to introduce to a statistic. Well, it's not a statistic; it's far more a mathematical approach to elaborate lexical profiles of characters. And this is called Barre's delta. Now, Barre's delta is essentially used for authorship attribution, and it's very effective and accurate. Okay, it works irrespectively with prose and poetry. And the way it works is the following. What you do is, if you have a writing which belongs to an unknown author, okay, what you do is the following. You compile a corpus, which is this one, the main set, and the main set consists of potential candidates that are the authors of this text. Okay, suppose that you have a text from the, 16th century, so you compile a corpus of plays or novels of the 16th century, right? You compile a corpus of each individual or potential author of the 16th century, which are somehow also entailed here, and finally the profile of the unknown play. Okay, once you have your corpus, right, with all the potential authors, you make a word list and rank the word list. Okay, and you focus on the most frequent words. Okay, to exemplify this, okay, now the analysis has been carried out with the 30 most common words. In this case, I'm just going to exemplify this. So the first thing you do is this. You establish the difference, okay, or the profile of each author with respect to the main set. So what this means is that, for instance, the indefinite article the occurs in the main set 4.2 times per 100 words. That is, it occurs roughly 4 times every 100 words, whereas a specific author uses it roughly 5 times. Okay, that's the standard deviation, and that's the set score. Don't worry about the set score, just about the score. So it gives you a profile of each author with respect to all the other authors of the period. Okay. Next, what you do is you specify in what way is the unknown play or the unknown writing different to the general corpus or to the potential, the whole set of potential authors. Okay, and here again, for instance, if you focus on the, you see that the main use of the is 4.2 for every 100 words, and here it's 4, it's a bit less, right? But you find interesting differences, for instance, here in the use of the preposition of, which is used roughly 1.8 times every 100 words, and here it's used 2.7 times, right? Which is far more, right? And finally, once you have established the peculiarity of each author with respect to its period and of the unknown writing with respect to its period, what you do now is you compare each author with the unknown play, right? And you calculate the differences. So you see, for instance, that the differences regarding the definite article the is minus 0.9, which means that it's roughly, it's this one here, right, is used far less in the unknown plane than this one here, right? So what you do is you create a profile of each author with respect to the unknown plane. Okay, or in other words, what you do is you calculate how different is each author in each of these variables with respect to the unknown plane, right? So at the end, what you do is you just sum up all the different or all the differences found for each variable, and the total sum, okay, gives you the most likely candidates. This means that the less the difference, the most likely the candidate. So you find, for instance, that here, if we had 5 authors, and this were the Barrow's delta, this is the delta, these are the differences found, the overall differences, you see that the greatest difference is in author 5. So it's the one which is probably the less likely to be the candidate of the unknown text, where in this one here, the difference is very small, so this is the highest candidate. So this is basically how it works. Well, the novelty about Barrow's delta is that we didn't use Barrow's delta to identify authorship, we used it to discriminate characters. If it's possible to use Barrow's delta to tell how different 2 authors are apart or how similar 2 authors are apart, if we use it for character discrimination, right, it will give you information about how distinct are the same characters within the same play. Okay, so as you know, characterization is a process of conveying information about characters, right? So we use the information, we use its speech, we use the words they say, we use the language of the individual characters, and we see how similar they are or how different they are. And in a way, we could also judge about the author's ability or author's genius of being able to describe characters in a very different way. And, right, so in a way, if the characters are very similar to each other, it means that there are no differences among the characters. And so in this case, we would accept the zero hypothesis. But at the same time, if the characters are very well developed, they might be very distinct to each other, right? Just ignore these are the statistics we use, Barrow's delta, but also additional statistics and regression models, okay? We focused on a play you might probably know, which is the tragedy of Hamlet, Prince of Denmark. I'm sure you know it. And we focused on the 5 top characters, Hamlet, Claudius, Polonius, Gertrude, and Ophelia. Okay, this is the information we got. That's the average of the play, and that's the characteristics of each of one. That's Hamlet, that's Claudius, that's the difference between Hamlet and Claudius, that's Polonius, that's the difference between Hamlet and Polonius, it's Gertrude, difference between Hamlet and Gertrude, there's Ophelia, his profile, that's the difference between Hamlet and Ophelia, and we also did it between Claudius, Polonius, Claudius, Gertrude, Claudius and Ophelia, Polonius, Gertrude, Polonius, Ophelia, and Gertrude and Ophelia. So we knew exactly the differences, the different profiles among all the possible comparison pairs. And this is what we get. The interesting thing is this: you have to look how this line declines. Now, the decline of the curve, we have this one here, the green one is comparing Claudius with Polonius. You see it declines. It means that if it declines, the more it declines, the two authors, the language they use, become similar. Okay, so if we were to take longer stretch, so it would actually decline to the very bottom, which means that the more text you use, the more similar they are. So in a way, it's logical because Shakespeare was the author. So Shakespeare wrote Hamlet and Shakespeare wrote Claudius, right? So you see that the authors are very similar. And from a linguistic point of view, there are very little, if any, differences among the different characters in Shakespeare, in Hamlet. Okay. Similarly here, there is a decline also if we compare Hamlet with Ophelia, right? This one here is a bit irregular because it's not Polonius doesn't actually occur very much at the beginning, right? But you see in all of them there is a decline, right? But the striking thing is, if we compare Hamlet with Gertrude, if you compare Hamlet with Gertrude, you see that there is not a decline, but there is a divergence, which means that the more text you have about Hamlet, Claudius, Polonius, and compared to Gertrude, the more distinct they get, which means they are very, very dissimilar. Gertrude is very dissimilar to the rest of the characters, at least the female. And finally, we compared Gertrude with Ophelia. And again, here you can see a very irregular curve, which means that the language used by these two characters is completely different. Now, what can we conclude? Well, we conclude actually that Hamlet, Claudius, Polonio, and Ophelia are very much like Shakespeare's language or Shakespeare's discourse. They're practically identical to Shakespeare. Now, the striking thing is Gertrude. Gertrude is a unique character. Now, the conclusions are various. I mean, you might think that the female characters have been far more elaborated by Shakespeare. Just consider that, for instance, female characters were not allowed to play in or to act in plays at that time, right? But the other striking thing is, what I think is that probably Gertrude was not written by Shakespeare at all. Gertrude was written by somebody else. And this explains why the language and the discourse of Gertrude is completely different to all the three male characters and also to the female character Ophelia. Okay. And I come to the last area of where mathematics can be used extensively, which is a very sort of novel area, which is culturomatics. Now, culturomatics, its goal is essentially to study human behavior or cultural tendency, right? The methodology is quantitative analysis of massive amount of digital data, texts and data, or also using meager linguistic corpora. The techniques are basically data mining and big data analysis. Okay. The information we have used here, which I strongly recommend you to use the Engram viewer. The Engram viewer uses 5 million books, which is roughly 500,000 million tokens, which is massive. That's a sequence of letters which is 1,000 times longer than the human genome. Or, in other words, if you would write these words in a straight line, it would reach the moon and back for 10 times, which is amazing, the information, right? Um, I strongly recommend you to read this paper by Lieberman and Baptiste, basically, which is quantifying the evolutionary dynamics of language, which is in Nature. It was published in 2007. There's also um, a, a TED video clip you can see, which is strongly recommended. It's very nice. It's very interesting. It's absolutely hair-raising. And the analysis I'm going to show you here, which is taken from the study of quantifying the evolutionary dynamics of language, is a longitudinal analysis of irregular verbs in English. Right. What these two people try to do is they try to study the regularization process of irregular verbs in English. They traced 170 irregular verbs from 800 onwards, right? And also they found that most of them, these regular verbs, became regular in 1200, 147, and the rest one, they analyzed them further on until 2000, right? And this is how the Engram view works. For instance, if you just type in these two forms, so the regular form and the irregular form, so you can see how they have been evolved and how they have been used. So you see, for instance, the throw, which was the irregular one, was more prominent from 18 to 1820. Then there was a drop here, approximately 1825, right? But it still was more used, right? And the difference was notably until 1900. But in 1920, there was a swap here, right? And the regular form, you can see that the regular form, right, is steadily growing, whereas the irregular form is steadily decreasing, right? And you can see here tendency, which is a very interesting approach, right? Now, what these guys did was the following. They classified irregular verbs, right, according to the frequency, right? So you have here 6 sets of frequency. You have the first one, which is be and have, which is the most frequent irregular verbs. Then you have come, to, find, and so on, which are the second one, the second category of frequency words. The third one, fourth, fifth, and sixth, right? And these are the number of regularities found for each case. So in be and have, there are no instances found of regularities. Here, none. In the third, they found 10 regularities, right? Here, they found 43, and so on. So you see that the regularities, okay, increase depending on the frequency. So the less frequent the word, the more likely this word is to become regular, right? And this is very interesting because they've calculated the approximate time these irregular verbs are going to last. So they established that be and have will last for at least 30,000 more years, 38,000 more years, right? Whereas others will be reduced to a lifetime of 300, right? The interesting thing is here. Okay, here we can see the different time spans, 800, 1200, and 2000, right? And you see that the number of irregular verbs decrease depending on irrespectively of the typology. So 6 typologies, all 6 typologies are decreasing in number. Okay, and if we take the decline of the different periods and the decline of the different typologies of irregular verbs, you see that there is a constant decline in frequency and regularizations. It means that the more frequent a word is, the less likely it is to become regular. Okay? So they established some kind of pace regularity of irregular verbs, and this means roughly that the survival rate or pace of regularity of an irregular verb is proportional to the square root of the frequency. So roughly, according to this slope, which is a minus 0.5 slope, it means roughly that every irregular verb that occurs 100 times more than another irregular verb, for each 100 more instances, it's likely to survive 10 more years as irregular. Okay, it's very funny. Okay, and just to finish up, I would just want you to tell you that, there are no mathematically and no linguistically gifted people, and here is a real evidence about this. Now, this evidence is taken from the SAT. The SAT test in the United States is quite similar to what we've got here about selectividad. And it has information, it's taken information about 1.5 million people. And what it says is that only five people that scored very high in linguistics or linguistic abilities failed mathematics. And furthermore, only 154 people who scored very, very high in mathematics failed linguistics. This means that these figures are completely irrelevant. This means that anyone gifted in language is also gifted in mathematics and vice versa. And just if I can do that, you can do it as well, right? And to end up, just let me quote as an epilogue some words by Stephen Hawking. He said something wonderfully like, "We have made remarkable progress in the last 100 years, but if we want to continue, our future is in space." And if we rephrase this, I would say that we have made remarkable progress in linguistics, but if we want to continue, our future is with linguistics. Thank you very much, and I hope you enjoyed it.